Welcome you all. Today we will start with a new topic, that is soil water. अभी बहुत भूल लिया हम लोग सॉलिड में, थोड़ा वाटर में भी घूमते हैं, इसमें भी तैरते हैं. जब सांस रुकने लगेगी तो फिर सॉइल एयर में पहुंच जाएंगे. ठीक है, लाइक दिस वे. तो वी स्टार्ट दिस टॉपिक. लेट अस फर्स्ट स्टार्ट विथ hydrological cycle, or you can say soil water cycle. Why? Because here you can see how in a cyclic way the water is getting distributed in soil and again lost, again coming to water, like a cyclic process. How this water operates, we'll see. Let's first draw a landscape picture. Here there will be plants. There are root systems. Okay. How now if we see, first there will be clouds, which will the rain will come. The rain will come, or if you apply irrigation, any kind of precipitation, just consider here on reaching the landscape it will infiltrate like this way. We can say this is infiltration. Infiltration is very simple, that is the downward entry of water. You can say simply downward entry of water. Some water infiltrates and some water gets runoff losses. After entering into the soil, what will happen? They will redistribute. So what will happen? Some will move vertically. We say it as percolation, and some will move laterally. Because as we already studied, how the pore space is not distributed in a regular manner. So there will be lateral movement, there will be vertical movement of water. We can say this seepage. Okay, this is rainfall. So after all this, we can say some water will be taken up by plants. Okay, and after runoff, it will deposit to your lakes, oceans, rivers, like river structure. You can say this is water. Okay, reservoir, water reservoir. Then some water will be used by your roots, and then it will go downward like this. And some water taken up by plants may get lost through evaporation, or rather we can say transpiration, because it is the losses are happening from the plant, so we can say transpiration rather. And here we can say evaporation. Here also evaporation occurs. If the plant structure is not there, the bare soil will be there. From soil structure only the evaporation will occur, so we can say evapotranspiration losses are there. Now the main important story is how this water distribute in a soil profile. So if we give imaginary lines as zones, the soil profile will be divided into mainly three zones. You can say first zone is your soil water zone, soil water zone, or we can say root zone. Okay, now just below to that root zone, we can see there is another zone. We call it as vadose zone, unsaturated soil water zone, or unsaturated we can say vadose zone, unsaturated vadose zone. Okay, let's just think like that. The soil matrices are like this way. So water distributed among themselves. Now this way, another zone come just next to your unsaturated vadose zone, there will be another zone. If I am drawing a imaginary line, it is not fixed. We can say this is your capillary fringe zone. Capillary fringe zone. After passing through this, now this is your unsaturated zone. This is your capillary fringe zone. After passing through this, now the water enters to your groundwater. We know groundwater charge is there, so this will be groundwater. From where we normally draw our drinking water, and also if no rainfall is there, if no precipitation happens or no irrigation is provided, plants take up water from where? This groundwater available with time. This is, we can say, groundwater. We normally, for our purpose, drinking purpose, we take water from this groundwater zone through tube wells, through those submersible pumps. Okay. So now if we see again, this is, we can say, soil profile zone. This soil profile zone in our soil mainly divided into 3 zones. Okay, one is your soil water zone or root zone, another one is your unsaturated vadose zone, and the next one is your capillary fringe zone. So the availability of water to this soil plant, we can say, mostly dependent on this zone. Or the recharge of your groundwater also mainly dependent on this zone. Okay, if this zone becomes very much saturated, then the water movement will be very less. Okay, just remember this is the important zone by which the groundwater recharge happens, and we can see this is a cyclic fashion, how water enters, then there will be population, there will be seepage, then losses of water happens through transpiration, or we can say evapotranspiration, then again this will come to your clouds, and there condenses, and sometimes this will again in form of rain coming to your surface. So simply this is a water cycle. We know without water there will be no life possible on the surface of the earth, and there are many importances for availability of your nutrients, for movement of your nutrients. There are many important points you can see with soil water. Also, you know, our earth surface is covered by 70% of water. Still 97% rather, you can say 98% of water is your undrinkable. Only very less amount of water is available for drinking purpose. Okay, still with this, after drinking also we are applying this kind of water also through irrigation. So water is very important to us. Now, as you have known, so let comes to know the next point, our molecular structure of water. Molecular structure of water. I think most of us know what the structure is, HOH, but we also know this water does not remain in this linear fashion. Rather, we can say it arranged these hydrogen atoms make an angle with the oxygen atom. This angle may vary. It may vary up to from 103 degree to 106 degree. Okay, but normally you can say this is 104.5 degree. Okay, so what happens now? One side you can see your positive charge and excess positive charge you can see, and one side you are seeing excess of negative charge. You might be knowing all this. This is very simple. I am just recalling your memory. So we can say this side development of your excessive positive charge, and this side development of your excessive negative charge. So this develops the water into a bipolar, or we can say polar molecule. This structure actually makes the water a polar molecule like this. What is polarity? We know polar means there will be no net zero charge. From where we can say here will go positive charge, there will go, here will be negative charge. So there will be no point of zero charge. Any point you choose in your water structure, you will get either positive or negative. So that's why this is polar molecule. So now we can say this is a polar water structure. So because of this polarity, this water molecule actually in liquid state makes your hydrogen bonding. If you see how this hydrogen bonding happens, let me draw a picture. We can say this is your oxygen to hydrogen atoms. Now the oxygen atom will attach to what? Hydrogen atom. This is a hydrogen atom. This is another hydrogen atom. This is, you can say, an oxygen atom. So now to this oxygen, now there will be attachment of hydrogen and another hydrogen. Like this way, we can say this is hydrogen, this is hydrogen, another water molecule attached here. Like this way, okay, like this way. Like this way, we can say the hydrogen bonding happens. In a water, simply at liquid state, we can say this hydrogen bonding happens. But if this water molecules becomes solid state, like your ice, this structure becomes what? This structure becomes open structure. Like this way, you can just. This is a 3D structure. So just imagine how this structure mostly develops. This way you can say here arrangement of 4 hydrogen atoms there. But generally here this is rather open structure. In case of ice, we can say this is rather hexagonal structure. Okay, this ice now becomes open structure, so this will float on the surface of the water molecule. So this is very simple, and because of this hydrogen bonding, there are many properties will develop in soil water. One property we can say here is dielectric constant. So what is dielectric constant? Dielectric constant simply resistance to electricity flow. So because of this hydrogen bonding, the water develops this property, and normally we say water having dielectric constant of 80. The value is normally 80. If we see another few properties, we can say this diameter of your water molecule is 2.64 angstrom. Okay, these are some memory based things you need to remember. Okay, and if we see another few most important properties, if we discuss another few properties, we will see one is your density. You know density? Density is simply by mass upon what? Mass upon your volume. So if we see, now we have discussed 2 to 3 property. If we see another property, I am writing 3. If we see density is simply mass per volume. So density of normal water is 1. Okay. the unit is now gram per cc or megagram per meter cube. We already discussed in our ball density, particle density, that's mass volume relationship chapter. So here normally this 1 gram per cc we have write at normally 25 degrees centigrade. This actually this density is highest at 4 degrees centigrade. Just remember, okay, the highest density of water achieved at 4 degrees centigrade. Now moving to the another important property, which I can say your surface tension. Surface tension. What is surface tension? We all know. We can say it is a property of water. So what it does in surface tension? Water does due to the force of cohesion and adhesion. We have discussed already what is the force of cohesion and adhesion. Because of this cohesion force, the water tends to shrink or occupy the minimum area possible. Okay, normally this is told in science. But and we know that the because of the surface tension force, the boat is floating on your water surface. The insect or we swim on above the surface of the water. If we come into soil, we can normally say it as force per unit length. Okay. If we come to soil, we see this is this is soil water. Okay, this is soil water. The water is on the rest. So this type of attraction happens, and another water molecule is here. Okay, now if we move this particle to soil, this is your soil matrix. Matrix I have said solid substances like soil solid. Okay. Now this water coming to this will form a thin film on the surface of the solid. And if the water now increases, what will happen? This is the force of adhesion. Because of the property of adhesion, this will stick to the solid surfaces. Now, if the water content increase, they will come in contact with each other. This is, you can say, cohesion. So what happens with surface tension? Here the tension was very low, or we can rather say zero. But coming here, the tension now increases for soil water. Or rather, we try to understand in terms of soil water potential. Along with surface tension, or we can say soil water potential. Along with this, some terms used like soil water tension, soil water suction. These type of terms are normally used and will be used in this soil water chapter. Just now here we will get the concept. What is soil water potential? Simply, if you see, this is a soil. Okay, soil matrix. If water is at a point A and water is at a point B, the water movement will happen from where? Because of soil water potential. We can say from higher potential to lower potential, from A to B. I would rather say it can move from B to A also. Why? Because the soil water potential is nothing but simple the energy status. You just, when this type of terms comes, you just remember this is talking about our energy status. Energy status. When there is more amount of water, what happens? The energy of that water will be higher, or we can say free energy. Here, the energy of water is free energy. So, this is highest energy. But coming to the soil surface, or rather we can say soil matrix, the water potential now getting decreases. So if the potential happens to be or energy status of water happens to be higher at A point compared to B point, then there will be movement from A to B. Simple. If consider in a condition, if the potential or energy status we can say at B is energy status higher. Energy status higher. Okay. So then movement of soil water will happen from B to A. It is very simple. And if we come to tension, here it was remaining with cohesive force, or you can say soil water with its threads. So there will be less tension as the soil water content decreases. There will be more adhesive forces compared to the cohesive force. So this will increase the tension. Just try to clear your concepts. In water potential, we are saying it is force per unit length. How this because of energy status, how much energy will be reduced compared to your free energy. In soil water potential, compare this. In tension, you say when the water content decreases, the soil water tension just increases because of adhesive forces. And in case of suction, it is also simply these are water is moving from higher to lower potential, but in downward flow, so there will be negative values are given. In case of soil water potential, there will be given a negative side. That's why it is called as soil water potential. And in case of soil water suction, simply the values are assigned positive. Okay, you think you are drinking a glass of water, a cold drinks, rather say. Okay, what happens when you are drinking? Okay, when the potential is higher, more quantity of water there will keep going, so it will easily you can drink. When you suck through the pipe, it will be easier get to you. But when this your soil drinks or your water decreases, then there will be difficult for you to suck, or more energy will be used to sucking the water. Like this way, when the stage happens, like this is a glass, some particles, last stage we have drunk all the water, but still some water are attached to this walls of your glass or drinking bottle. So to suck this quantity of water, you need more energy. Like this way, we have seen more addition will be there instead of cohesion. So this way, just analogy with soil water, you can see the soil water potential. Now I think you get the concept. Now we can say in surface tension we assign the value. Now normally for soil this value becomes 72.75. Let me say 75 dyne per centimeter. Okay, if you want to give it in terms of SI unit, you can say 72.75 into 10 to the power minus 3 Newton per meter. Very simple. Okay, this value you just remember. And coming to capillarity. Capillarity we know. Capillarity is normally what happens. I have drawn that figure like this way. You can draw. This is soil water. And if soil acts as a capillary, so there will be tube-like structure formation in soil. Okay. This is although this is not straight. I have already told. We are assuming here the straight tube-like way, so that we can calculate. Here you can say rise of soil water is there, and it makes this angle theta. Okay, this is you can say pressure of air above the water air meniscus, and here it is the pressure of water, and this height of rise is given by h. If the height of rise is given by h, this is surface of water, and PC because so capillarity is mainly the rise of water or there is fall of water because of surface tension. We have discussed what is surface tension. Because of surface tension, always remember this surface tension is most important in your soil water chapter. Because of surface tension, so if we see the downward force, here, we know force is simply what? Force is your mass into acceleration, or you can say acceleration due to gravity g. This m is your, we can say, density equals to mass upon volume. So this becomes your density into volume. So if you write the your downward force, the volume becomes your pi r square x. Okay, volume becomes your pi r square x, and you can say density of water from this and acceleration due to gravity. This is your downward force. If you see the upward force acting, just it looks like a cylinder. You can easily write this formula. Coming to another your upward force, you can say the circumference will be 2 pi r, and it will be multiplied by your surface tension and the angle it created, which cos theta. So at equilibrium, when you at equilibrium, the upward force will be similar to your downward force. So at equilibrium, if you see at equilibrium, what will happen? This pi r square h will, and your density of water into acceleration of gravity equals to 2 pi r, your surface tension cos theta. Okay. Now if you solve from both the sides, okay, this r h r, you can say 2 cos theta, 2 into surface tension into cos theta by r x rho g. Okay, this much now we know, but here we can put the values. We have assumed, as we have already assumed, surface tension normally for water is what? I have already written in Newton per meter square. If we keep this in terms of 1 unit, you can say 72.75 into 10 to the power minus 3 Newton per meter. And your cos theta, what is theta? Let's assume your theta is 0. Okay, because normally water surface we assume 0. So this cos theta will be your 1. Assuming theta equals to 0, here equals to 0, this cos theta will be 1, and your density of water is your 1. Okay, and your gravitation, acceleration due to gravity is 9.81 meters square per second. Okay, by putting all these values, now you can conclude this r equals to 0.15. Just put those values, we will find this type of value. Your r equals to, we can say 0.15 by h. Yes, sir. H equals to, rather you can say 0.15 by r. Okay, you just solve all this, you will get this type of equation. Okay. So, and we know r is your d by 2. We can also write this equation as h equals to your 0.3 by d. In this way, we can see how if the radius of your capillarity is very less, then the rise will be more high. It is inversely proportional. So we can see if the radius is more less, the rise will be more high. As we can see in case of micropores, the size is very less, so the radius will be very less. As we are considering it as a sphere, so the height of rise will be easier, or capillary rise will be more. Okay, but in normally we see the pores are not uniform. If the pores are not uniform, okay, if the pores are not uniform, we can see from here only I am drawing like another capillary. there will be another capillary. In this way, if you see, I am drawing this way. Okay, there will be, here it will be your obtuse angle, here it will be acute angle, like that way. If you see, here it will be angle created, here it will be angle created, and the radius will not be same. If you see, this is one of the sphere, and there will be radius R1. Here we give R2. You can see, and here one scientist, his name was Laplace. He gave an equation for this. We can say, as per the Laplace equation, I have already explained this partial pressure of air and the pressure of air. This is, you can say, the pressure of air above the air water meniscus, and this is the pressure of water below your air water meniscus, or we can further say in water. So if we consider this equation was Pw minus Pa equals to your 2 into surface tension of 1 by R1 plus 1 by R2. Sorry, you can say this equation was given by Laplace. Okay, and later he considered this R1 and the R2, if we call it as R. Okay, if you call it as R, given as equivalent radius. Equivalent radius, then the equation becomes like this way. Here given the equation. Just remember, this is kind of memory based questions are asked mostly. So here we can say, in terms of your R, if the value of this mean radius or equivalent radius, you can say equivalent or mean radius, rather in terms of mean radius. Okay, so if we see, if this value of R comes positive, then the if it is lies in water phase. If this value comes positive, then it lies in your water phase, and if this value comes negative, it lies in your air phase. Okay. Now coming to another important property, which is viscosity. What is viscosity? Viscosity, it is simply, you can say, a resistance to flow. Okay, so water molecules, when resist to flow, we can say it is highly viscous, and it given by equation, you can say viscosity is given by equation F equals to viscosity into A into this is differential velocity function. Okay, from here we can solve the velocity value. Okay, we can find the velocity value, and normally at 25 degree the value is your 0.0089 points. This is directly asked, what is the unit of viscosity? You can write points, or we can say it as dial second or centimeter square. This is its unit. From this unit, if the dimension is also asked, we can write it. Okay. Now coming to this much property, you just remember, these are the major important properties, like your surface tension, capillarity, contact angle, your viscosity, your dielectric constant. These will be discussed in further concepts what we will discuss in soil water, this property will be used. Now if we see soil water availability, as you have seen there are three zones. So if we see soil water availability, or rather you can say retention of water, how this retention of water happens, we see retention of water. We have already seen this is mainly due to the property of your adhesion and your property of surfacetension. These two main property determines the retention of water. In surfacetension we have seen the soil water potential, all these terms. So here we will discuss that. Let's see if there is a soil. Okay, soil profile, you can say a soil, and the rain happens or any kind of precipitation were given, more irrigation is given. All the pores now in soil will be filled with water. We have already seen how soil matrix is there. This is your pore. Okay, so when you apply more water, this will be, all the pore spaces will be filled. Like this way, you can see if rainfall happens or irrigation is given, then all the pores will be now saturated. Or we can say here, can say this is gravitational water. Gravitation. Okay, can say this is your gravitational water. We'll discuss that. Or we can say that it is saturated soil. Now just think of a post texture soil. The post texture soil after 24 to 36 hours, then the water will be reduced. As we have discussed, there will be evaporation, there will be seepage, like this way, or there will be evapotranspiration. That is this way, this water loss happens. So after that, a point happens which is called as field capacity. It is normally achieved in case of post texture soil within 24 to 36 hours. Normally we say in field condition, and in case of your high texture soil, in clay soils, this achieved in your 2 to 3 days. Now the water is at its field capacity. Here the water potential was 0. Okay, soil water potential, can say here the soil water potential was 0. But in case of at field capacity, okay, we can write here the potential becomes 1 by 10 bar. We will use this water potential units like bars, atmosphere, your kilopascal, like this type of units we will be using to demarcate. And this is in case of your post texture soil. In case of high texture soil, the potential will be your 1 by 3 bar, or you can say 0.1 bar, and it is 0.33 bar. I have already told why the negative sign I am giving. Okay. Now you see, after some time again, there will be a point achieved where the cells became turgid, and the if you plant starts wilting, जो कहते हैं हम लोग मूर्छाने लगेगा. ओके, सो सी this is we term as permanent wilting point. This is imaginary line I am drawing. Okay, if we say permanent wilting point, and sometime there will be another point we will call it as hygroscopic coefficient. Okay, and here the water now becomes very much reduced. The water that only stays like your arsssoil. Arsssoil water due to the more aggressive force, here only this type of water remains. Okay, now there will be another point where we can say air dry soil. Lastly, we can say open dry. Here there will be no water in any form. Okay. And if we see the potential values across this permanent melting point, we can say the potential will be soil water potential will be minus 15 bar. Actually, the soil water potential are generally in terms of metric potential. We will discuss later how the soil water potential is varied with metric potential, your osmotic potential, with your gravitational potential, pressure potential. We will discuss that. Now, coming to hygroscopic coefficient, here we can say the soil water potential value is your 31 bar, minus 31 bar. Okay, you can see as your water content is decreasing, the potential value is also decreasing, and your soil water tension is increasing. And in case of air dry soil, we can say that minus 1000 bar. In terms of kilopascal, you can write that is normally 1 bar equals to 100 kilopascal. Okay, and 1 atmosphere equals to normally 0.9 bar, or you can say 1 bar. Okay, 10,000 bar. This is, and we assign another value here, which is called as PF. What is PF? PF, like pH, it is the negative logarithm of hydrogen and activity to the base 10. Like this way, you can say PF is your log of height of, okay, you can say this is the height of this H is your you can say suction in centimeter of soil water column. Suction in centimeter of soil water column. Or simply we can say PF is the force with which water is held. The more force it held, the PF value will be higher. If the water is in your free state, like in your saturated state, the PF value will be 0. As the water content decreases, there will be more PF value, because this will be held more tightly because of this adhesive forces. Okay, and you can say here in terms of suction. Suction, what is suction? I have already told. The more amount of suction it needs, like I have given the example of drinking cold drinks. The more we suck, okay, the less will be water. If the less water, then more energy we have to invest to suck the water. Like that way, we can remember the PF value as if this saturated condition will be 0. Okay, and in case of your field capacity, we can say 2.58, and here we can say 4.2. Here 2.54 is right, 4.2 the PF value, and in case of hydrological coefficient, the PF value is your 4.5. This you have to remember, because these are some memory based things. You understand here and remember also few points, so that it will be easier for you. And at air dry value, the PF will be your 6. You can see how the PF value is increasing because of water content is decreasing. And we can say at open dry, the PF value becomes 7. Okay, this is the PF value. And if you want to physically classify this soil, we can say here the water is fully saturated at this condition. The water is fully saturated, so the water will be not available for plant use. Simple, or we can say free flowing water. We can say free flowing water. Okay, now we are classifying this soil as the basis of availability. We can say this water is not available. Now, when the soil exists at a point of field capacity, then the water availability to plant actually starts. From this point to this point, we can say this is your available water. From field capacity to permanent wilting point, we can say this is your available water for the plant. By upon reaching the permanent wilting point, the plant actually starts to wilt. If you provide also water, then the plant will not recover. Before permanent wilting point, there is a point we call wilting point. Okay, so at wilting point, when you just start to see the symptoms of wilting, if you give water and rather manage it well, then the plant can recover. Okay, this is I am telling because of irrigation scheduling. All the soil water concepts are studied because of mainly of irrigation scheduling. We have to schedule irrigation because water availability is most important to plants. So next, if you see this available water, now if you see the capillary water, you can say this is from your field capacity to your hygroscopic coefficient. You can say it as capillary water. Okay, because of water remaining in your micropores after field capacity. Here it was remaining more in macropores, but after field capacity the water retention will be more because of micropore dominance. Okay, so this will be your capillary water, and from this point to this point we can say this is actually your unavailable water. From your permanent wilting point up to open dry soil, we can see this is called as unavailable water. This way, a conceptual diagram, if you see this conceptual diagram, the most of the concepts will be clear and you can remember this in a well constructed manner.